Today we want to continue picturing two-dimensional surfaces in three-dimensional space. And we started off with looking at planes, two-dimensional planes in three-dimensional space with linear equations. And now we're going to degree two equations in up to three variables. And it's going to give us a quadric surface, a generalization of a conic section. We're going to use conic sections to help visualize the level curves of our quadric surfaces. I need to find a way to shove more math words into that sentence. That way I could use it as a background if you're writing some scene, right? Like you have a scene in a movie where some math is supposed to happen, so you're supposed to write some math on the board. The best thing to put up there, if the movie is not too technical, just put some algebra 2, or it's not some algebra, but some calc 2 up there, some integrals and stuff. You've got integral symbols, maybe a Riemann sum.
Well, no one.
Yeah, most people won't recognize that because most people haven't done calc 2. And then you just put a person standing in front of the board, dressed slightly strangely, talking way too animatedly, because that's how the general population views math nerds. It's like, oh, wow, look at that fancy math. And like calc 2 students like, oh, that was my homework, like the first week of calc 2 several years ago. Anyway, what are we talking about? All right, so let's take a look at some quadric surfaces. I'm going to go into a very difficult to find resource. A very difficult to find resource, but very excellent. It has the pictures that I said that you're not going to want to have to picture all the time, and it pairs them with different kinds of equations. What we want to do is we want to grab one of these surfaces, take a look at the picture of the surface, and then see what different level curves are going to look like. We're going to imagine the different level curves. So just like with everything else on Wikipedia, there is way more detail than we need. That's always going to be the case. Look up parabolas, and it's like not appropriate for students that are in algebra just trying to learn how to find the fucking vertex, right? And they go, it's too much information. That's why math textbooks exist. But let's okay, Euclidean plane. This seems excessive, but that's the game that we're playing. Oh, there's a quadric surfaces, and then we scroll down and we see pictures like, oh, yay, now it's a comic book. So we're going to start with some non-degenerate real quadratic surfaces. The real part just means we're not allowed to use complex numbers. So get out of here with the complex numbers. That's for complex analysis. That happens in a couple of semesters. What we want to use these for is to take a look at our general equation and the description of what it is, and think about what the level curves look like. We're going to think about intersecting a plane with each of these surfaces. So non-degenerate real quadric surfaces. So we're not going to do all of them in class. We just want some examples of what we're doing. Non-degenerate real quadric surfaces. Remember, what we want to see, oh, you can't see what I'm writing. So the first one that we see here is called an ellipsoid. X squared over a squared plus y squared over b squared plus z squared over z squared over c squared. We had to make all the letters names rhyme. Really annoying. So x squared over a squared plus y squared over b squared plus z squared over c squared is an ellipsoid. There's the equation for an ellipsoid. What we want to do is take a look at a bunch of level curves. What are the level curves going to look like? So the reason that we get away with just one generalized conic section, take an ellipse, becomes an ellipsoid, is that every slice, every which way we slice it, we're always looking at an ellipse. For constant values of x, ellipse. Constant values of x, ellipse. Constant values of y, ellipse. Constant values of z, ellipse. For those of you watching the video, I had my hands going in the wrong direction. I mixed up my x and y. Because I was going like this when I should have been going like this. And I thought, this doesn't work on the radio. Well, watch the show. So every fixed value of x, we're going to be looking at an ellipse. Similarly for y and z. So if x equals constant, I'm just kind of combine all this into just one constant. Actually, no, I need to. I know I wrote the word constant, and then I used k for constant, so we're just going to use the mortal constant. K. So notice, once we make a fixed value of x, we have an equation in y and z. That's going to be a one-dimensional curve in two-dimensional space. And we see we get an ellipse, or we get nothing. What do I mean when I say we get nothing? Note that if when we have x squared over a squared, on the x-axis, the largest x value we'll see is a. The smallest x value we'll see is negative a. That's like the x radius is a. So from the center, we go a in one direction, a in the other direction. After that, the surface stops. There is no surface. So note that that shows up here in the equation, because I've got the constant x or y squared over b squared plus z squared over c squared is 1 minus k squared over a squared. If that constant k is equal to a, then I get y squared over b squared plus z squared over c squared is equal to 0. We just get a point. If we make k greater than a, if k goes greater than a, if we go outside of where we see the ellipse, then we get y squared over b squared plus z squared over c squared is equal to a negative number. So if we grab a value of k, that's greater than a, then we get y squared over b squared plus z squared over c squared is equal to a negative number. And since we are looking at real quadric surfaces, we get nothing. There are no y and z that fit this description. No real y and z fit this description. There are no real values of y and z that fit this description. For real y and z, y squared is positive, z squared is positive, their sum must be positive. Y squared is non-negative, z squared is non-negative, their sum must be non-negative.
At this point, give you what?
We start allowing complex numbers, then we got a much more complicated thing to picture. Because if we have complex numbers for y and complex numbers for z, remember complex numbers are two-dimensional. There's a real part and imaginary part. So I've got the real y, the imaginary y, real z, imaginary z. So we are in R4. We're trying to get something that's isomorphic to R4. And now it's very hard for us to picture because our puny three-dimensional consciousness is kind of trapped in three dimensions. Any questions? Is everybody okay? So we see this ellipsoid. When we see this equation, no matter which variable we make constant, we get an ellipse, an ellipse, an ellipse. Ellipses for constant x, constant y, and constant z. Let's go grab another one. The next two, we got an elliptic paraboloid and a hyperbolic paraboloid. Elliptic paraboloid and hyperbolic paraboloid. So we got two different types of paraboloid. So what we want to do is look at the two things that could happen. We either have the elliptic paraboloid or a hyperbolic paraboloid. Look what happens to one of the variables. What's happened to one of the variables in our paraboloids? And it loses the z squared. One of the it doesn't have to be z, it's just the one that we chose to put like I was there. The one that was chosen for these examples. It could be that x is degree 1, y and z are degree 2, and that would just take our elliptic paraboloid and turn it 90 degrees. Or if y is degree 1 and x and z are degree 2, that would just take our elliptic paraboloid and turn it 90 degrees some other way. It just depends on which way we're going to see those ellipses. But we get a paraboloid when one of the variables is degree 1 instead of degree 2. And we have two varieties, an elliptic paraboloid and a hyperbolic paraboloid. Notice that if we make constant values of z in our elliptic paraboloid, we get ellipses. Because we have x squared over a squared plus y squared over b squared equals z, which would be a constant. We get a bunch of ellipses. If we make z constant in the hyperbolic paraboloid, x squared over a squared minus y squared over b squared equals z. That's going to be our constant. We're just going to have a different, we're going to have a hyperbola. Any questions? So we have these two kinds of paraboloids. Elliptic if we make z constant, we're looking at an ellipse because the x squared and the y squared will have the same sign. And then we'll have the hyperbolic. In this case, I went with a plus x and a minus y, but we could also have a minus x and a plus y. And that would just turn our hyperbola 90 degrees. So what we want to notice here is that we get ellipses for a constant z. And in our hyperbolic paraboloids, we get a hyperbola for constant z. Otherwise, we get parabolas. If I make x constant, I got z and y squared. That's going to make a parabola. With both the elliptic and hyperbolic paraboloids, we see that for certain values of z, we won't get anything at all. If z is 5 over here and we subtract it, or like a plus 5, and we subtract it, x squared over a squared plus y squared over b squared equals -5, we don't get anything because x and y are need to be real. That would be values, that would be when we are beyond the edges of our ellipse. For the hyperbolic one, there's like a hole in the middle. Oh wait, no, I was thinking of something else. I was thinking of the one sheet ones. So our paraboloids are parabolas for 2 of the variables being constant, and either an ellipse for the third one being constant or a hyperbola for the third one being constant. Our paraboloids happen when one of the variables is degree 1 instead of degree 2, which happens to be the same time we get parabolas instead of ellipses or hyperbolas when we're dealing with conic sections. Parabola happens when the degree y is 1, degree x is 2, or degree x is 1, degree y is 2. One of the variables drops down to degree 1, parabola. Both of them degree 2, ellipse or hyperbola, depending on the signs. How's everybody okay? Got ellipsoid, we got paraboloid, and of course we're going to have hyperboloid. Hyperbolic paraboloid, hyperboloid of 1 sheet and a hyperboloid of 2 sheets. Let's take a look at what we've got with these different hyperboloids. So when we're looking at the hyperboloids, notice that we've got x squared, y squared, and z squared. So we're all back up to degree 2. That makes sense. If we're going to be like all hyperboloid or ellipsoid, we're going to have everything be degree 2. If one of them is degree 1, we're going to be all parabola something. Paraboloids or parabolas. Depending on which variable we cover, right? Which variable is that we're going to have 2 positive and 1 negative, or 2 negative and 1 positive. We write that in this different way. So one way to describe it is this. This is the most common way. I prefer to think of it as 2 positive, 1 negative, or 1 negative and 2 positive. So notice I've got x squared plus y squared minus z squared equals 1. This is the most common way of looking at it. If I take out the z squared, make that constant, then we have an ellipse. If I take out the x or the y, then I have opposite signs, and I've got a hyperbola. If we look at the hyperboloid of two sheets, it's equal to -1, which looks different than, because it's always been equals 1. If I change the -1 to a +1, then I'll have a -x, -y, +z, 2 negatives and 1 positive. That's different than the previous hyperboloid of one sheet, where it's positive, positive, negative, 2 positive, 1 negative. Number of sheets is equal to the number of negatives. I'm gonna write them down. So with our hyperboloids, we have two varieties, one sheet or two sheets. That's the number of negatives, 1 or 2 negative. One negative, one sheet. Two negatives, two sheets. Or you could think of the same thing with a -1. Look at we can think about our cross sections. Fixed values of z, we get ellipses. Fixed values of y, hyperbola. Fixed value of x, hyperbola. In two sheets, if we just fix the value of z, then we get kind of empty space unless we have the large enough z values. So that when we subtract the z squared over c squared, the 1 that we subtract from 1, and we get a negative on the other side, then we have this gap for a certain range of z. For z between -c and c, we get nothing. But then the hyperbolas start, or then the ellipses start. That's why we get two sheets. That's why we get that gap between the top part and the bottom part. If our z is between -c and c, then this 1 minus z squared over c squared will be positive. And our equation will be like minus x squared over a squared minus y squared over b squared is equal to a positive. And that's why we're not getting anything. No real x and y fit this description.
Real numbers.
Real numbers include negative numbers. But when we take a real x and square it, we get a positive. Then the negative makes it negative. Take the real y squared and y and square it, and we get a positive. The negative makes it negative, so we get more negative. So that left side cannot equal the positive right side. No real x and y fit this description. That's why we have those two sheets. That's that separation based on the value of C. Once Z gets bigger than C or less than negative C, then we can start to have some values. Then minus x squared over a squared minus y squared over b squared will equal some negative, and we just cancel out the negatives and we're looking at an ellipse. And that's what we see when we look at the images. Any questions? How's everybody okay? These are all the non-degenerate quadric, real quadric surfaces. Notice that sphere never came into it because sphere is just an ellipsoid where x, y, and z are all the same. Sorry, where a, b, and c are all the same. So we know the equation for a sphere is x squared plus y squared plus z squared equals r squared. So a sphere is just a special case of an ellipsoid. Any questions, comments, snide remarks? What we're doing is we're taking our equations of degree 2 in free variables, and we're just thinking about what the level curves look like. When we take out one of the variables, when we just make one of the variables constant, we want to be able to look at that and say, bunch of hyperbolas. Take one of the variables and make it constant and say, bunch of ellipses. So we can see what these cross sections look like. We can imagine what the contour map is going to look like, what the topographical map is going to look like on this hyperboloid of one sheet. We also want to be able to look at the form and decide what the shape looks like. We see the x squared y plus y squared minus z squared equals 1. That's a hyperboloid of one sheet. And we imagine what that hyperboloid of one sheet looks like. Kind of like that tube that's skinny and then gets fat. Hyperboloid of one sheet. Ellipse is in one direction, hyperbola is in the other two directions. How's everybody okay? Difficult to talk about this because I'm not allowed to read your minds to find out if you're picturing things correctly. It used to be so much simpler. I'm like, well, everybody picture what this looks like during the test. I'd be like, well, everybody picture what this looks like. You don't have to write things down. You start picturing it and I start reading your minds. You actually don't have to put your fingers on your head to read minds and make little noises, but people feel better when you do that. So like just to indicate, that's like a visual indication that I'm scanning minds. I go, and everybody has to come up with their own. Some people are like, oh, wow, 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 wow. And then they're reading your minds. You know what I'm talking about? I don't know what you do when you're reading other people's minds. I'm just kidding. I'm not allowed to read people's minds anymore. Oh, wait. I'm kidding. I can't read people's minds, is what I'm legally supposed to say. I'm just kidding. I totally can't do that. I totally can't do that.
Well, never mind.
I mean, comment? Sorry. I'm also not allowed to predict the future. So it makes it really difficult because students be like, oh, when am I ever going to need to know this? And I like sit there and I look into their future. I'm like, oh, never. Or I look into their future. It's like, oh, next semester you're going to be repeating this class. So then you're going to need to know it. By the way, you're going to flunk this class again. So I'm just totally not allowed to do that. It's kind of, it's really annoying because I could really streamline this whole process. And people would just be like, oh, when am I ever going to need to know this? It's like, oh, well, unfortunately and I pick out like the 4 students, You four are actually going to become teachers. And you're like, oh, no. And I'm like, oh, yes, I know. You're going to be fresh out of college. You'll need the money. And that's that you're just going to have to do that. Oh, man. And then you're like, oh, please tell me at least I'll be teaching at college. I'm like, oh, no, you're going to be teaching high school. And they're like, oh, no. And I'm like, oh, I'm changing my major. Oh, it just got better. You're going to be a millionaire. All right, so that's what we want to do. This was just the Wikipedia entry for Quadric surfaces, an idea about how we want to things. Notice that I left some off, the degenerate ones. I want you to think about your conic sections and your quadric surfaces and making things constant. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.